Please Look Up is recorded at SciTech on Whadjuk Noongar land. Good evening, everybody, and welcome to Please Look Up, the monthly podcast produced by Particle, where we take you through a guided tour of the night sky as seen from Perth, as well as taking a deep dive into some of the more out-of-this-world space news. In this episode, we'll be discussing what you can see in the night sky in the month of September. My name is Leon, and I'm joined by Amanda, a professional presenter from the SciTech Planetarium. Amanda, thank you for being here.
No worries, thanks for having me.
Welcome back. You were here last month as well.
Yeah.
You seem to be our resident expert in all things space and astronomy. Now, as we always do with these podcasts, I'd like to start by asking you, what planets can I see if I'm outside in the night sky looking up?
Yeah, well, as it has been the case for the past few months, Mars is still up at sunset. It is the last chance to catch it up in the western sky at sunset. So if you want to head out and check it out, you can by looking out where the sun sets, and you'll know you're facing west, and you should see Mars up there for the last time this month for a little while.
Yeah, I've been looking at Mars. It's super faint right now, isn't it?
Yeah, exactly. So if you want to go check it out, it is still up there, but what I recommend is that you turn 180 degrees the opposite direction so you're facing east, and Saturn will be up rising in the eastern sky, looking very bright at the moment and somewhat yellowish. And if you want to wait around until 10 p.m, Jupiter will be rising as well in the eastern sky. Now,
good.
Yeah, if you want to wait around even longer, or maybe go to sleep and then get back up in the morning, at sunrise, you will see Venus rising just before sunrise in the eastern sky, and later on in the month, Mercury will be joining Venus there as well.
Wow, so it's all in the east this month.
Yes, it is.
Okay, I think I have seen Saturn because stars, they are very much whitish when you look at them in the sky, but I have noticed something's kind of yellowish in the east. That's probably Saturn then?
Yeah, particularly if you're looking in Perth, stars do look primarily white. They do actually have colours, but the lights of the city of Perth do wash those out, so they tend to look pretty white. Saturn, however, will look yellowish.
Yellowish, radio. And Jupiter at about 10 p.m, did you say?
Yeah.
Yeah, okay. Okay, that's good because I'm definitely more of a night person. But so Venus is now the morning star, I guess, if it's...
Yeah, exactly. So we talk about it as the evening star when it's that first star, but we know it's not a star, of course, that appears in the night sky. And when it's up just at sunrise, we call it the morning star.
All right, so yeah, Venus is the bright thing in the morning before sunrise, and Mercury said in the second half of the month, is that right?
Yeah, later on the month, you'll see Mercury joining Venus in the morning.
Oh, in the morning, okay. Oh, that's good to know. All right, so it's all about the planets in the east this month. Is there like a best day to go out, or does it not really matter?
Well, I suppose it depends on what you mean by that. A good time to go out is when there isn't the moon up, because the moon, it reflects a lot of light from the sun. So it makes it more difficult to look at the stars and the planets. So if you're out on the 29th of September, which is when our full moon is, not great for planet and stargazing, but you will get to see the full moon squidged between Saturn and Jupiter, which can make for nice viewing.
Oh, okay. So yeah, normally you wouldn't really go looking during a full moon, but just by coincidence, it happens to... Are you saying that like you'll have the full moon and then on one side there'll be Saturn, on the other side there'll be Jupiter?
Yeah, exactly. So we know all our planets line up because our solar system is kind of flat.
Yeah,
so they all pass through that ecliptic, we call it.
Yep.
So they all kind of line up when they're near each other in the sky, and the moon falls on that same path. So it just happens to be between Saturn and Jupiter in our night sky. So it might make them easier to spot in that they'll be lined up.
Yeah, that's pretty neat. Just a coincidence that the full moon is position between them this month.
Yeah, but if you're particularly interested in looking at the planets or maybe constellations, I'd recommend 2 weeks before that when the moon's not going to be up, so you can see better.
Yeah, that makes sense. That makes a lot of sense. Okay. What about any interesting constellations or stars? What's hot this month?
Yeah, okay. Well, if we are talking about going out perhaps during a new moon where the moon's not up and we can see some stars, we might want to look for a fainter constellation. Mm-hmm. For example, Pavo, I find, is a very exciting constellation. It is a giant space slug.
A giant space slug. Pavo the space slug.
Yes. You're looking at me like you don't believe me, and that's probably because, Leon, you keep hearing the story of Pavo the peacock.
I've heard of Pavo the peacock, yeah.
Okay, and if anyone at home is using apps like Stellarium on their phone to go look up constellations, you can do that. You can go find Pavo in the night sky, and an app might help because it is quite faint. And that app will tell you it's a peacock.
Yeah, let's go and spin me a story then.
Seeing if you can connect the dots to make a big body and then make two sluggish antennas, and then you can see a giant space slug in the sky.
Wow.
I think it's a very important lesson that pictures don't really matter.
The pictures don't really matter.
You can make up whatever you want, and I definitely choose to see a giant slug when I look at Pavo. We really just use the constellation names so that we know what we're looking at. So as long as we're all calling those ones Pavo, for example, if I want to talk about the particular star Pavo Delta, then I'm talking about the fourth brightest star in the constellation Pavo.
Right,
so that's why we need to know constellation names.
So the naming is important as far as using it to name stars and so on.
Yeah.
But just because people call it a peacock doesn't really matter.
Yeah, some people hundreds of years ago decided it's a peacock. It's not that interesting.
Yeah.
Definitely look for a space slug.
Okay.
But you might also try and find Pavo Delta, particularly if you're using stellarium, that'll be a bit more helpful. And it's a pretty cool star. It's very high in metallic elements.
Mm-hmm.
Now, Pavo Delta is about 20 light years away from us, and we haven't found any exoplanets around it. But the reason is exciting is because looking at data from where we find exoplanets around different stars, so exoplanets are planets orbiting around other stars, not our sun, we see them more often around stars with high amounts of metal in them. So haven't found them around Pavo Delta, but it's a bit of an interesting star because it is more likely that it would have exoplanets given the kind of makeup the star has.
Wow, that's a lot to digest in one go there. Firstly, I'll just bring it back a second where you said it's a faint constellation, so it is actually probably useful to use something like an app to help you find it.
Yeah, definitely.
Because it's not going to stand out like Orion or Scorpius.
Yeah, this is where I fully confess that if I'm looking for Pavo in the night sky, I use an app because especially in Perth, it is very faint.
Yeah, okay, good to know. Delta Pavo it's a star that's got like higher amounts of metals, and that correlates with the probability we'll have planets. Is that what you said?
Yeah, based on looking at other stars.
Oh, looking at other stars that we know have planets, and then looking at what the star is made of, and we tend to find higher metals in those stars, and that means we might find, there's a higher chance of finding something around Delta Pavo.
Yeah, based on our previous observations, we would predict it probably does.
Oh, that's really cool. All right. Well, I guess I'll have to have a look for it, the Delta Pavo in the big space slug.
Exactly.
I believe Pavo is ancient Greek for phoenix, not phoenix, for peacock.
Again, all semantics. You could call it whatever. Well, we're going to call it Pavo so that we all know what we're looking at.
Right, but the artwork?
I definitely see a slug.
Okay. Sure, all right. I know what I'm looking for now. All right, well, is there any other interesting space news in September?
In space news, well, coming up we do have the September or spring equinox.
Yes, the equinox. I knew that was around about now.
Yeah, exactly. So,
what happens on the equinox?
Equinox is when the sun passes directly over the equator. So Earth is sort of on a tilt, usually.
Yes.
Upward is on a tilt.
Yep. I see what you mean. So usually the sun is either slightly towards the north or towards the south.
Exactly. But this is where in Earth's orbit it takes it so that it's directly over the equator. And that basically equi meaning equal and nox meaning night. We have equal night and day. So 12 hours for night and day is the main part.
Oh, okay.
So if you were exactly at the equator, you would see the sun right up overhead and your shadow would be directly underneath you. It wouldn't stretch out in front of you or behind.
Right, and this is on the day of the equinox.
Yes, exactly. And if you're at the equator. Obviously in Australia, we're a bit further south, so we won't experience that exact phenomena on an equinox.
Yeah, gotcha. And what day is this? What's the date of this equinox?
So exactly it's on the 23rd of September.
Oh, right, okay. And is this, I'm assuming it's related to spring?
Yes, so obviously for us in the southern hemisphere, because we're heading towards summer, and so with our equinox we have spring. Our spring equinox. And so then as time goes on, you'll notice for us, the sun gets even higher in the sky as we head into summer. So as the sun is getting higher and higher in the sky through spring and into summer, we have more sunlight per square metre of ground area. So you can think of it as it's more intense amount of sunlight, and that's why it's warmer for us. And then the northern hemisphere is experiencing the opposite. So that's why they're going into their colder.
Right, and it's all because of the tilt.
Exactly.
Good to know. The International Space Station is always a big hit. Are there any good predictions for when's a good time to go and look for the space station?
Well, I'm not a night person, so I have a few times you can look for it. For example, on the 17th of September at about 5:30 a.m.
I'm not doing that.
Or the 20th of September at just before 5 a.m.
Okay, oh God. So the 17th and the 20th, and you said 5:30 on the 17th, and just before 5 on the 20th?
Exactly. Now, you might not be a morning person, so you can always just look up, where can I see the ISS? Always could just type that into Google, see if you can find a time that's more suitable for you.
Right, I might have to do that, but that's good to know. Okay, so for anyone who likes torturing themselves, then you can get up at that time of day
Yep.
and go for a look. Fantastic. Let's leave Earth behind for a bit then. is there any other interesting news in the big wide world of space? What's happening?
Yeah, there is. So the ISRO, or Indian Space Research Organisation.
Yes.
You might remember from last month's podcast,
they're
we
all
talked
in the
about
news right now.
Yeah, exactly. So Chandrayaan-3, obviously, big news. They did successfully land.
They landed on the moon.
From lander. Yes, a soft landing. So they touched down softly. Were able to deploy their rover that's been roving around for a couple of weeks.
Yes, I did see the footage of that, of the camera on the side of the lander as the rover drove down onto the surface of the moon.
Yes, so that's exciting news, but they don't stop there. They have also launched the Aditya L1 spacecraft.
Oh, okay. They didn't even take a break. They just
straight into it. They launched that on September 2nd, and it was over to go study the sun.
So Aditya L1 is off to study the sun. How's it gonna study the sun then?
Yeah, so it's got 4 cameras on board that are special telescope cameras, and they're able to look at the different layers of the sun's atmosphere, and it'll also be looking at the magnetic field from Earth and solar flares coming from the sun, and it's going to look at how those things interact and what effect the sun is having on Earth.
Oh wow, that's pretty ambitious. So it's viewing the sun from a distance with its telescopes, and then it's using its magnetometer and whatever at Earth to see what's going on.
Yeah, so it has a magnetometer that'll be near Earth, and it's going to be looking at the magnetic field here on Earth and to see if the magnetic field is impacted by the solar flares coming.
Wow, that's a hugely ambitious mission.
Yeah.
I look forward to seeing what comes out of that. So you mentioned that Aditya L1 is going to be observing the sun, but it's going to be measuring magnetic fields and activity near the Earth. So where's Aditya L1 actually going to be?
Yeah, so fun fact, it's actually in the name. Aditya L1, the L1 refers to Lagrange point 1, and that's where we're sending this telescope.
Oh, right, it is in the name. Okay. It's cool, but this might be a stupid question. What is Lagrange point 1?
Yeah, it's actually a really good question. So basically you have Earth, and Earth has its own gravity. So you know how you can put objects into orbit around Earth? So like the moon is naturally in orbit around Earth, and we put satellites into orbit around Earth, and that's because of Earth's gravity. Well, we also know Earth is in orbit around the sun, which has a lot more gravity, of course, and that's how Earth stays in orbit around the sun.
Yep.
But you can think of those 2 points in space. Earth's gravity is pulling towards Earth, and the sun's gravity is pulling towards it.
Yep.
So there's this point in the middle where the gravity actually kind of stabilizes.
Oh, right.
And that point is much closer to Earth because the sun's gravity is much stronger.
Right.
But even though there's no object there to create its own gravity, we can still send things out to this point called Lagrange point 1, and we can put them into orbit around this sort of gravitationally stable point that occurs there.
Right.
So that's where they've sent it out into orbit around this point, and then it therefore orbits around the sun in time with Earth as Earth moves around the sun.
That's really clever, isn't it?
Yeah, and it's not the first time we've seen this done. You might have heard of Lagrange points when we were talking about L2, so Lagrange point 2, when the James Webb Space Telescope was launched. So that was launched out past Earth to Lagrange point 2 at that stable point, but we wanted it to be shielded from the sun, so it was away from Earth.
Oh, right, okay. So yeah, I do vaguely remember hearing about L2 when reading about the James Webb Space Telescope. So this is L1, which is in between. And it's kind of intuitive, isn't it? Yeah, you've got the sun pulling in one direction and the Earth pulling in the other, and everything just kind of cancels out.
Yeah, exactly.
And it's just a nice chill region. Okay, is there any advantage to that? Is that just to get a good look at the sun?
Yeah, well, it's a nice stable place where we can put the telescope. Obviously, we don't want to send it into the sun. That wouldn't be great.
Yeah, right.
But this point also means that it travels through space alongside kind of Earth. And what we're wanting the telescopes on board, or the magnometer, to do is measure the magnetic fields of Earth as well. So we're talking about how we want to be able to compare what's happening in the magnetic field with what's going on with the sun. So being in this position allows it to be taking readings of what's going on with the magnetic field on Earth as well as what's happening with the sun.
Right, okay, so it's close enough but not too far. All right. You said it's going to study the layers of the sun's atmosphere. What layers does the sun's atmosphere really have? I'm familiar with the corona. I saw that a few months ago up in Exmouth, but what else is there to it?
Yeah, okay, exactly. So you would have seen the corona. For people who didn't get to go up to Exmouth and see the eclipse. The corona, meaning the crown, is sort of the sun rays around the sun. And if we talked about the eclipse, it's that bit we can still see when the moon goes in front of the sun.
Yeah, it's like on the front page of the paper, or like the stereotypical photo of the eclipse is this dark circle in the middle and then the corona on the outside.
Exactly. Now, if you then think about looking at the sun with your eyes when there's no eclipse, which you shouldn't do, that's not great for your eyes.
Bad idea.
If you were to do that and you looked at the sun, the light you can see coming off of the sun is coming from the photosphere. Photo meaning light, and sphere because it's round. So the photosphere is not actually that thick. It's about 100 kilometres thick, and that's where all the light that we see comes from the sun.
Whoa,
yeah.
So 100 kilometres thick.
Yeah, so that part isn't actually the outer layer of the sun near the corona. Yeah. There's something above the photosphere which is called the chromosphere, and this is a region of plasma, basically. It's ionized hydrogen around there, and it's actually thicker than the photosphere, so it's several thousand kilometres thick as opposed to 100 kilometres thick.
Yep.
But you don't really see that. What we're seeing is the light from the photosphere.
Well, okay, so the chromosphere is kind of almost transparent.
Yeah, exactly. To our eyes, it's just this plasma region around that is there before the corona.
Wow, okay, so just to check that I've got this right, so if we're looking at the sun, if you're taking a dive into the sun, you've got the corona on the outside, that sort of wispy thing, the wispy tenuous part. Go a bit deeper, you get the chromosphere, this sort of several thousand kilometres of plasma, and then the photosphere, which is about 100 kilometres thick. And that's where, just to get did I hear that right? All of the glaring brightness of the sun that we see is emitted within that 100 kilometre thick layer of the atmosphere.
Yeah, that's where the light comes from. And so those kind of upper layers of the sun is what this mission is going to be studying.
Wow, okay, I gotcha. And if I remember correctly, the sun's a 1.5 million kilometres across or something. So this really is just the outermost several thousand kilometres of the sun.
Yeah, exactly. So obviously the sun is huge, and we really are only studying those upper layers. We're not getting too deep in here with this mission. Okay,
so we really are just studying the very outer layers of the sun. And while we're on that topic, I've heard the corona is a bit weird.
Yeah, they're probably talking about it when you were looking at it up in Exmouth during the eclipse. They might have mentioned that.
Yeah, might have heard one or two things about it.
Yeah. The really weird part is that the corona is incredibly hot. And you're probably going, yeah, okay, it's the sun. It's a star.
Yeah, of course it's hot.
Very hot. And the sun sits at approximately, we say the temperature of the sun is 5,700 degrees Kelvin.
Right, so that's of the photosphere.
Yeah, exactly. So that kind of level, which is about the same as 5,700 degrees Celsius approximately. At those ranges, all the scales sort of are the same. But the corona is millions of degrees.
Millions of degrees?
Millions of degrees. So it's hugely different. It's not just a little bit hotter. It's off by a scale of 1,000. And the reason that is so weird is because you can think of Earth, and our core is where all our heat is on this planet. And as you go out towards the edge of Earth, it gets cooler. And that's kind of what we expect to see typically. But as you move away from the sun... As you get
further from the sun...
It gets hotter.
It gets hotter for a bit.
Yeah.
That is bizarre. And you said, I see what you mean. It's it's not just 2 or 3 times hotter. It's thousands of times hotter as you get further out. That's really weird. Yeah, if I think about that, because let's use kangaroos as an example. A typical kangaroo might be 1 metre tall, and if you see a big kangaroo, maybe 2 metres tall, it's just a big kangaroo. But if you saw a kangaroo that was 1,000 metres tall, then that's suddenly some fundamentally different biology going on. So in this case, you've got the outer part of the sun is 1,000 times hotter than the sort of the surface. So
yeah, and in the same way, that would be it's fundamentally different physics.
There's some different physics going on.
We're still trying to really figure out why that is, and it's part of what this mission will be looking at.
Wow, gotcha. That's very cool. So how exactly is a DTL-1 going to be studying these different layers of the sun?
Yeah, okay. So I mentioned it had 4 different cameras on board.
Yeah.
So the first one is a coronagraph, which images the sun's corona. There's also a UV imaging telescope. So that'll be what they're using to look at the photosphere and the chromosphere.
Right.
And then there's also 2 X-ray instruments on board. So the solar flares that come off the sun are these kind of intense localized bursts of radiation, and they tend to be in X-rays.
Oh, right, gotcha.
And there's also coronal mass ejections, which are large eruptions of plasma ejected away from the sun.
Yep.
So both of these things are strong sources of X-ray, and scientists do think that these strong eruptions of X-rays are potential explanation of what's causing that corona.
The corona heating.
So
right.
by looking at them, we might be able to start understanding a bit more about what's going on with all that heat in the corona.
Okay, wow, that's okay. So a bunch of different instruments to study those different layers.
Mm-hmm.
Gotcha. I've seen like videos, or I think from NASA, of like those coronal mass ejections where there's just these huge eruptions, and you put Earth for scale, and it's like 20 times the size of the Earth or something like that.
Yeah, exactly. If you've seen those images online of those big plumes coming off the sun, that's what we're looking at here.
So Aditya L1 can image different layers of the sun's atmosphere and the sort of activity that's going on at the surface, and then what?
Yeah, so the idea is to take all of that information, and because we know when it's happening, we can draw correlations between when things are happening in the different layers to see if there's a relationship between what happens in one layer and then what's happening in another layer. So particularly, for example, we talked about those coronal mass ejection or solar flares. If something then changes in the corona, we can see that they might be affecting the corona.
Oh, I see. And because you can image them all at once, you can tie activity between the two.
Yeah, exactly. And that would represent an area that we could then look into further with investigation to study that particular relationship.
Yeah, I got you. And then is the intention to carry that correlation further to try and measure effects at Earth, given that you said it's got like a magnetometer and solar wind detectors on board the spacecraft? Is that also going to try and relate to what's going on at the sun as well?
Yeah, exactly. So we're interested in how the layers of the sun relate to each other, but then, of course, we're measuring the activity of the magnetic field on Earth. So we're wanting to see how all of that data we're gathering from the layers of the sun relates to what we're seeing on Earth, and if there's any relationship between the two.
Yeah, okay. So it's almost a complete end-to-end. You have activity at the surface of the sun, which may affect activity in other layers of the sun, and then ultimately you may even be able to track that all the way to local effects near the Earth in the solar wind or the solar magnetic field and things like that.
Exactly.
So it really is the whole end-to-end spacecraft mission.
Yeah, there's a lot going on. They don't rest.
That's really clever. And yeah, I like the fact that after successfully landing on the moon, the ISRO didn't even stop for a break before launching a solar mission. Wow. Well, I look forward to seeing the data that comes out of Aditya L1 over the next 3, 4, 5 years. It must be out there for a while, I'm imagining.
Yeah, this one's going to be a much longer mission than the Chandrayaan lunar mission.
Yeah, it was only a couple of weeks, I believe. Wow, there we go. Well, that's it's been a time and a half. That's been a great conversation. Thank you so much for coming here today, Amanda. I feel like I've learnt a lot. It's been a pleasure.
Thanks for having me as always.
That's it for this episode of Particles. Please look up. We'll see you next month where we talk about the night sky and the space news for October.
If you want to hear more interesting space news, check out the website particle.scitech.org.au for more information.